Here are the facts we've just established about the standard normal distribution. First, we established that 1 over root 2 pi is the right constant to put in front of the density to make it integrate to 1. And we did that in a probabilistic way. We didn't integrate that function and show that it is equal to 1. We looked at two independent standard normal variables and compared with a different random variable that we'd got in another context and realized that this constant has to be 1 over root 2 pi to make things work out. We also showed by integration that absolute z has a finite expectation. We actually found that expectation to be square root of 2 over pi. And because the expected absolute z is finite, therefore z has an expectation, and once it has an expectation, then you can add and subtract in any order, and you can cancel things. And so by symmetry, the expectation has to be 0. And the reason we did this work, the reason we didn't just say, well, the density is symmetric about 0, therefore the expectation is 0, is because of the cautionary tail of the Cauchy distribution, which is also symmetric about 0, but doesn't have an expectation. So we had to do this work. And we also showed that the expectation of z squared is equal to 1, and so the variance comes out to be equal to 1. And so these parameters, the center and the spread, that we have been calling the mean and the variance, turn out to actually be the mean and the variance of the standard normal distribution by our general definitions of what a mean and a variance are. And while we're about it, let's just note that if x is some other normal, then of course x is a linear transformation of a standard normal. And so by linear transformation facts, sigma times 0 plus mu, which is mu, the expectation of x is mu, and the variance is sigma squared. And so now we have a genuine justification for calling the parameters of the normal the mean and the variance respectively. And while we're about it, let's list some other facts that we have found out about the normal along the way. These are very useful for calculation, so it's just a good idea to have them in one place. Number 4. Somewhere in an earlier section we showed that z squared has a gamma distribution. In fact, you did part of this as an exercise. We also showed that if you take two IID standard normals, then the radial distance Israeli. And while we're writing things down, the density and by integration or other means, the CDF At this point, it's worth going back to chapter 1 and taking a look at the exponential approximation to the chance of at least one collision in the birthday problem. And you will see that you have a very similar functional form. And lastly, because the Rayleigh is the square root of an exponential half random variable, we have z1 squared plus z2 squared is exponential half, which is a fact that we'll see again in a different way in a couple of sections. And all of these facts pop up all over the place. It seems like a bit of a laundry list now, but gradually you will get used to using them all.